Let's start with a mass on a spring attached to a wall. So we got a wall over here, got the floor, we got a spring attached to the wall, and a mass attached to that spring. Starts out at some equilibrium position. And we are either going to scrunch that spring, compress it toward the wall, or grab it and pull it away from the wall. I should say we do it to the mass, but the spring, of course, affects things. Take that mass and either push it toward the wall by compressing the spring, or grab it and pull it away from the wall. It doesn't matter for our purposes today, which thing you do. You can either compress it or stretch it. It doesn't matter. Pretend X is the amount that you either compress it or stretch it as a positive quantity. Okay. Let's let X equal the amount of compression or stretching. It's possible to think about both compressing and stretching, and mass going back and forth, and X being a displacement. Say positive to the right when you stretch and negative to the left when you compress. But I'm trying to keep things simple and ignoring that and just thinking about doing one of these things. This gets a little tricky to think about. Let's pretend we're stretching. So you grab the mass and you're pulling it. If you were to try to pull this at a constant velocity, you have to keep applying more and more force because of the spring. Because the restoring force of the spring gets larger and larger the more it gets stretched. You have to keep applying more and more force. If we're going to stretch it and hold it somewhere and not move it, not let it go, we have to apply a force against the spring as well. And that depends on how far it's been stretched. The further it's been stretched, the more force we have to apply to hold it in place. That force is proportional to the amount of stretching. It's some constant of proportionality times the amount of the stretch. K times X for some number K. K is called the spring constant. Spring, if I can spell spring. Spring constant. I like making cursive Ks, yes. Spring constant. Its value depends on what the spring is like. Is it a really thick, stiff spring? Then K is large, right? It's difficult to stretch it or compress it. Or is it like a slinky? Very easy to stretch it or compress it. K would be small. You might wonder, is this a perfect model? It's called Hooke's law. It's actually not a perfect model. It's reasonably good for small amounts of stretching or compressing. But once you get close to the breaking point, then all bets are off. But we assume this is true for small amounts of compression or stretching. What's the goal? The goal is to use this idea to try to figure out the work done if I stretch it a certain amount or compress it a certain amount. What's the work done? This is tricky as well. Think about it this way. Imagine you say stretch the spring to a certain point, X. You're holding it there. You want to stretch it a little bit more, like that. The amount extra that you stretched it is small. The force is effectively constant over that small amount of stretching because the change in position is so small. You could say delta F. Let's see, how do I want to think about this? No, delta W, the small amount of work necessary to stretch it a tiny bit further is an approximately constant force times a small amount of distance. This is an approximation because the force is only approximately constant times that small amount of distance. What is that approximately constant force? Use K times X. K times X times delta X. That's the small amount of work necessary to stretch the mass a tiny bit further. To find the total work to take that mass starting at equilibrium and stretch it a long ways, but not near breaking point, you have to add up these little works. Approximated by a sum like this. And that, once again, we have is a Riemann sum for whatever function's there, in this case, K times X. I'm not specifying K, I'm not specifying what the spring is. If you know it takes a certain amount of force to hold a spring in a certain spot, you can figure out what K is. You can use this equation. By the way, F is in newtons still. X is in meters, and therefore K is in newtons per meter. You can effectively take the force and divide by X to figure out K. But I'm thinking about this without figuring out K. Let delta X go to 0. The total work becomes then an integral. Integral of K times X. To get an answer, we want a definite integral. If I'm starting at the mass at equilibrium, X equals 0, and pulling it a certain distance, say D, it would be an integral from 0 to D. You could have particular numbers for both K and D. This gives 1/2 kx squared. X goes from 0 to D, which gives 1/2 k d squared. That's the answer for the total work done to stretch it from position 0 to position D, where K depends on the spring. This can be thought of in a way that's pretty intuitive, actually. If you rewrite this expression as K times D over 2 times D, maybe with parentheses like that, what I really have there, K times D over 2, is like an average force times the overall distance. Right? The force at equilibrium is 0. The force to hold it at position D is K times D. K times D over 2 is the force to hold it halfway between 0 and D, the average overall force. So this is saying you can figure out the entire work done by taking the average force times the distance. In this situation, at least, it may not be so clear what to do in more complicated situations.